Thank you very much. It's also a pleasure to be here. It's very exciting because these are current topics that we are researching actively in with colleagues, with collaborators, and so on. So this is a glimpse into what is going on there. I was told that I should ensure that this works well for a mathematically literate but still general audience. So I hope I can toe this line here. Feel free to interrupt me at any point. Also happy to take questions afterwards, but I don't want anyone to be stuck with something that they completely disagree with, or where I'm saying something very wrong. All right, we're going to start with some brief graph learning paradigms in machine learning. And just to get all of us on the same page here, graph learning refers to taking a graph and then learning some kind of tasks on it. These tasks could be, for instance, the classification of the graph itself, of the nodes, of the edges, and so on. So, for instance, the graph itself could be a molecule that you want to synthesize, and then you want to classify whether this is a toxic molecule for human beings or not. You can also do regression tasks, regression referring to the prediction of certain properties, oftentimes continuous properties. So to stay in the molecular regime, you could ask, how easy does this molecule dissolve in water? And again, you can do these on the graph level, on the node level, and on the edge level. Likewise, you can do the edge prediction, or sometimes also known as link prediction, where I give you a graph and you take two unconnected entities in that graph and you say, no, they need to be connected because of whatever reason. So for instance, predicting friendships in the Facebook graph, even though I don't think anyone uses Facebook anymore, apparently, so a little bit dated, that reference, or predicting other kinds of interactions between human beings. And then a last task that is kind of interesting is given a distribution of graphs. So for instance, a set of molecules that you already know are good for certain drug combinations, for instance, you want to compare this with another distribution of graphs, for instance, arising from a machine learning model that you trained. So one of the big things in this graph learning with all these tasks, and this is something they all have in common, is that these graphs need to be represented somehow to make them amenable to machine learning algorithms and to any kind of computational algorithms, right? And one issue that you will always run into is that the two graphs can have, in general, a different number of vertices. So you're not even, I could just add a few disconnected vertices, and then you would run into some issue when you have fixed size representations. So what people are doing is they are learning kind of maps to vectorize these graphs. So this is a very general way of writing this, and it's not, it could be more precise, but I want to just give you a general, just an overview here. So you vectorize a graph. That means you take the graph, you map it into some fixed dimensional vector space, and then you compare the images of the graphs under this map instead of the graphs themselves, with the idea that this mapping somehow represents graph similarity or graph edit distance, or can serve as a proxy for the similarity. And one thing that you will always encounter when you delve into the machine learning literature here is that this map needs to be oblivious to the ordering of the graph entities. This is known as permutation invariance. The idea being that you can set up the graphs, you can enumerate the nodes in one way, or you can reverse that enumeration, or you can permute it, or whatever. And of course, you don't want your representation to depend on the node ordering. That's really important. That is something that kept the graph machine learning community busy for quite some time. There are a couple of typical algorithms that are being used, and I already apologize in advance because I won't be able to give you a lot of algorithmic details here, because we want to talk about curvature, and the graph neural networks and all the other graph task and learning algorithms, they only play a small role in the background. But I want to give you a taste of what is going on in the community. Roughly speaking, there's two houses, like in Romeo and Juliet. There are the shallow approaches, there are the deep approaches. None of them is necessarily any better than the other. It depends very much on your application and what you want to solve. Shallow approaches, for instance, comprise the really famous node-to-vec, which essentially vectorizes your nodes using an encoder-decoder architecture. Of course, they also comprise things like graph kernels, which I particularly like. There's a survey around there which I wrote during my postdoctoral research. It's juicy mathematics because it's about reproducing kernel Hilbert space feature maps. So that's something that I enjoy. Then there's also embeddings based on operators on the graphs. For instance, the most famous Laplacian-based embeddings, where you take a graph Laplacian and then you use that for embedding. On the other side, you have these very recent techniques on graph neural networks. I'm using this term in general to mean all kinds of neural networks, but we'll see that there's a specific class that we are specifically interested in. These deep approaches, they comprise, for instance, graph convolutional networks, graph isomorphism networks, and graph attention networks. The exact and precise differences are really, really hard to enumerate in such a quick overview talk here, but I'll do my best to at least give you an idea of the paradigms that are going on. And the predominant paradigm that you'll encounter all the time here is message passing. In message passing, you take your graph and neighboring nodes can exchange messages. So these messages are typically also vectors in some d-dimensional vector space. Doesn't have to be necessarily the same d as the graph embedding, but typically it is, right? And they are then aggregated using some kind of permutation invariant functions, such as a sum or a mean and so on. And by doing this in a fashion that makes this aggregation differentiable or trainable, as the machine learners like to say, you end up being able to learn various representations of your graph as you iterate this process. So just as a brief example, you start with node D here, you take a look at its neighbors, B with a message X, message Y, and a message Z respectively, and then you aggregate these messages together, maybe together even with a message that D has attached to its nodes. So this is kind of the rough overview of how this message passing works. And the moral from the mathematical point is that by iterating this process, you can indeed get informative global representations of the graph, despite only doing local operations or local measurements. And that is also my personal segue into curvature and why curvature is useful. This is now a little bit detached from graphs, but we'll get back to graphs in a few minutes. So curvature is, I would say, one of the most exciting and also elusive concepts in mathematics, because there's just so many definitions of that depending on where you're looking, where you're focusing on, right? And in general, curvature is about characterizing how curved an object is, right? This object could be a surface, a manifold, a topological space. Important thing to notice here is that curvature can either be extrinsic or intrinsic. What we are most interested in, I would say personally, is intrinsic curvature, because the curvature should not change with respect to the embedding or with respect to the way you represent your data. There's, of course, a famous notion of curvature, which was developed by none other than Gauss himself. So this Gaussian curvature, the product of principal curvatures, this works well for surfaces, and it is indeed an intrinsic property of the surface that's known as the theorema egregium, so the surprising or the exalted theorem. There are also these classical model spaces that you will always see. These are, I would say, the nice intuitive concepts behind the different curvature regimes. So in negative curvature, you have these hyperboloid surfaces, or the saddle surfaces, if you will. In flat curvature or zero curvature, you have the plane, which is the epitome of flatness, right? And in positive curvature, you have the sphere, which is the quintessential example of a positively curved space. Now, there's two geometrical characterizations which help us understand curvature a little bit better. They are due to Gromov and Ricci respectively. I don't want to give too many references here because we want to get back to graphs really quick, but just as an understanding, negative curvature is often characterized by saying that geodesic triangles in this space are somehow thinner than reference triangles and are seen to exhibit angular defects, so their angles don't add up to 180 degrees. You can see this on this saddle surface, for instance, where if you think about increasing the curvature even more, or rather I should say decreasing it even more, then you will find that this triangle becomes thinner. Likewise, on the sphere, it becomes kind of thicker, right? The other characterization of curvature that I personally like is due to Ricci, or is relevant for Ricci curvature, namely in positive Ricci curvature, the corresponding points, using a concept known as parallel transport, which is not relevant for this specific talk, but just so the people in the know understand what I mean by this, in these corresponding points of spheres, they are then closer than their respective centers are. So just as an illustration, in a flat regime, you have corresponding points and they're exactly as close as the centers are, right? So no surprises there. But if you do the same thing on a positively curved space, so on the surface of a sphere, for instance, you will find that the upper geodesic between the corresponding points is closer than the respective centers actually are. So this is kind of our notion that will propel us forward and make it possible for us to extend curvature to the graph regime. Why is this actually useful? Well, in the manifold setting, we can answer this question relatively easily. I mean, I know that I'm in a mathematically inclined audience here, so I don't need to do too much heavy convincing here. But one thing that convinced me about the utility of curvature is that it's a local quantity, but it still gives you global characteristic information about a manifold. So you have the Gauss-Bonnet theorem, for instance, which is still mind-blowing to me in that it puts together a purely geometrical measurement that is local, namely this curvature, and a purely topological component that is global, namely the Euler characteristic. There's also Bonnet-Meyer's theorem, which will crop up again later on, which basically tells us that if we can compare the Ricci curvature and if it's bound from below by that of a sphere, then we also know that the diameter is bounded from above. So we get some very nice geometrical insights into our manifolds when we look at curvature measurements. And this is something that will keep us going and that will be retained for the graph setting as well. Now we finally arrived at graphs, and this is where things get interesting, at least from my point of view, because graphs are a little bit harder to characterize. So in graphs, when we're dealing with a graph, we think about just a structure that has vertices and edges, fair enough. We also assume that the graph is connected. This makes it a little bit easier because otherwise you have pairs of points or pairs of vertices, I should say, that cannot be reached from one another. And this is a little bit tedious to handle. So we just assume that this is not the case. Now, graphs, as we all know, also lack kind of a smooth structure. I mean, we could consider them to be simple geodesic spaces, but it's really, there is no concept of smoothness directly on the graph. So we require a different treatment in terms of curvature. There's two notions that I want to present to you. I would say the second one is arguably more important for this talk, but the first one I'm presenting as a purely combinatorial concept. It's known as the Forman-Ricci curvature. And the second one is a little bit more aligned with respect to optimal transport ideas. We'll get to that in a few minutes. Again, let me repeat the question that I showed before. Why is curvature useful? So now we're in the graph setting. We're not in the manifold setting anymore. Giving some pointers here to previous work and to ongoing work in the machine learning world. Please feel free to check that out. I won't be able to discuss these aspects in great detail, but I think it's important to know who has done something and to point out relevant work, of course. So first of all, graph curvature actually can be used to explain training problems in graph neural networks. So it turns out that negative curvature edges are really problematic for this message passing flow. This is something that Topic and colleagues have researched and analyzed in a very great paper on understanding over squashing and bottlenecks on graph wire curvature. Finally, this type of issue can also be revisited with an Ollivier-Ricci curvature, and it turns out that the same issues apply and you get even more precise bounds. That's a very exciting preprint that recently dropped on the archive by several of my colleagues. Now, in my own work, we also found that graph curvature serves as a characteristic property that can simplify graph learning tasks. This is a paper that we'll be discussing later on. It's about the Ollivier-Ricci curvature for hypergraphs. It's a unified framework for that concept. And finally, a preprint that used to be under review, but it just got rejected from a machine learning conference. Going on record with this, it's such a shame. That's on curvature filtrations for graph generative model evaluation. So these are the two publications that we'll be discussing in the remainder of our time here. Now, that brings me to Forman-Ricci curvature. Just a quick overview here, how this can be calculated and why it's useful. In Forman-Ricci curvature, you define a curvature per edge. It's a combinatorial formula that is essentially 4 minus the degrees of the respective nodes plus 3 times the number of 3 cycles, or rather triangles, that are incident on the 2 nodes. If you do this for our simple graph here, this is, by the way, the example graph that will accompany us throughout this talk, then you find that we get low curvature or negative curvature at some of the edges, whereas parts of the cycles, for instance, have almost flat curvature. So bottom line, it gives us a little bit of a better insight into how this graph looks. But I would say in this specific case, it's not something where I would say, oh, this makes intuitively much more sense than any other measure. We'll see whether this remains true for the Ollivier-Ricci curvature as well. Now, this brings me to this great notion of curvature, which is due to Ollivier. It was described, first of all, for Ricci curvature of Markov chains on metric spaces, but people soon realized that this is a very nice notion of curvature that can be easily extended to the graph space. And this is where it's now, I would say, being predominantly used, at least in the machine learning world and the network science world, to my understanding. The notion is relatively simple. So you assume that you have a graph, you have a shortest path metric D on this graph, and you have a set of probability measures mu v for every vertex. And then you define the Ollivier-Ricci curvature of any pair of nodes, where, with the understanding that you don't define this for the node with itself, right? You define this as 1 minus a weighted quotient of the Wasserstein, the transport distance between the two probability measures, divided by the actual distance within the graph. So for instance, if you have edges in the graph for which you calculate this curvature notion, then dij, so this second term here, will of course be 1, right? Because they're connected. But this guy here, this term here, can of course be different. In particular, I want to stress this here. I didn't put the formula here for clarity's sake, but this Wasserstein distance is a so-called optimal transport distance, and it essentially tries to match or transport the probability mass of the first probability measure to the probability mass of the second probability measure with costs that are equivalent to the respective distances within the graphs. So it is not just a statistical measure that is only looking at the probability measures, but it has some notion of the geometry and topology of the graph, because it knows how to actually do the transportation along the edges of the graph. And I would say, or rather parroting Ollivier here, I would say that this is in some sense the natural generalization of Ricci curvature to a larger class of objects, because it gives you kind of this idea of checking whether your corresponding points are closer than the centers are. And as I said, this was quickly adapted for use in the graph setting because it has a very nice conceptual simplicity. Now, it also has a very nice set of properties. Namely, we have a nice lower bound. So it turns out that it's sufficient to know the values of this curvature measure for each of the edges. So if we have a lower bound for the edges, then we also know that this is a lower bound for the non-edges in the graph. That's great. Moreover, we get what I like to call Bonnet-Myers-like theorem. So it's not exactly the same, but it tells us something about the diameter. It gives us a bound of the diameter. I don't want to spend too much time going into the details here, so I'm rather moving on and want to briefly talk about how to actually pick this probability measure, because that remains the most relevant parameter in this setting. So the normal practice, the common practice nowadays, is to define this probability measure for each vertex based on random walks out along that vertex. So taking a laziness parameter alpha, you essentially remain at your own node with probability alpha, and then you distribute the remaining probability mass equally uniformly among the neighbors of a node. And this is already sufficient to give you a very nice insight into the graph. The idea here why you don't pick higher order neighborhoods is that this is really supposed to mimic the idea of curvature being a very local property of a manifold, even though, of course, you could extend that measure. And in fact, it might sometimes be useful to extend that measure, but more about that later. And moreover, with this definition, you have nice bounds for the Ollivier-Ricci curvature. You have bounds that are between -2 and 1, and you get a very nice Bonnet-Myers bound for the diameter of the graph as well. So what are the canonical examples of this curvature measure? Well, previously we had the saddle surface, the plane, and the sphere. And here we have, I would say, a kind of graph-like equivalent of these model spaces. So for negative Ollivier-Ricci curvature, we have tree-like structures or hyperbolic structures, if you will, where the idea is that you have only a few walks to reach from one node to the other node, right? In flat curvature is characterized by a grid graph, so something that is very, very uniform in all directions, and positive curvature is characterized by something that should now look a little bit like a clique graph, like a fully connected graph. I know that this guy is not fully connected, but I wanted to indicate that it might become fully connected. Now, this figure is inspired by a great paper on discrete curvature on graphs from the effective resistance, which coincidentally produces and describes yet another curvature measure called the effective resistance, but it has different properties and we won't be able to cover that here. Well, some examples in particular, since you have this alpha parameter, this laziness parameter for the random walk to pick. So this is the same color map throughout. What you can see is that starting from the right-hand side, if you have a very high laziness, so you never move away from your nodes again, then you will find that this is basically zero curvature everywhere. So it doesn't give you a pretty good insight there. Interestingly, with non-lazy random walks on the left-hand side here, you do get some insights, right? So it's not, you always move away from the vertex at which you are at the moment. You can find that, for instance, the edges here are a little bit attenuated, and the cycles also appear to be somehow highlighted. What people typically use is just something in the middle, namely alpha equals to 0.5. And there you can see that this, I would say this choice, not sure whether it's the best choice, right? It depends on your application, but at least you can see that this gives you a very strong highlight of the edges of the leaf nodes here in this specific graph, whereas it kind of tries to align the two cycles with each other in terms of their overall distribution. Again, let me stress, the actual choice depends on your application. There's no right or wrong choice here. Maybe the only wrong choice would be alpha equals to 1, because that would mean that you don't walk around in the graph anymore, and you can't tell the difference between individual edges anymore. But other than that, you're good to go. Now, this brings me to the first application, because we're interested in applications, right? We want to see what can we do with this notion of curvature in practice. And the first application I want to briefly talk about is the comparison of graph generative models. This is also where we get some interesting new mathematics on computational topology, for instance. Namely, the problem that we have is that we are given a distribution of graphs, and we're given different models for generating new graphs. And now what we want to see is how close or similar, if you will, in the distributional sense, these two distributions are. So whether they, in a perfect setting, we would just be reproducing all the graphs that we have already seen, right? Then we would have a very, very strong similarity or closeness, if you will. If we are reproducing something completely different out of, so for instance, we're learning Ollivier-Ricci graphs, and we always just give back fully connected graphs or something like this, then we would have to have a very, very low dissimilarity, low similarity between the two distributions. Now, there's a lots of applications here for I would say the dominant one is drug and molecule design, where you use the drugs and molecules that you already know are working or relevant for a specific task. You feed them to graph neural network or to a graph generative model, and then you try to get new compounds back, and you now think about, okay, are these good compounds? Can I trust the model's output, and so on and so forth. There's also road networks, of course, or vessel networks in the eye, for instance. If you ever go to an eye doctor, I'm not going to pronounce the Greek name here because this is on record, but if you go to an eye doctor, then they often make images of your vessels in the eyes and check them for degeneration and so on. And having a way to compare two distributions here, for instance, between sick patients and healthy patients, is a very good way and will increase patient well-being, hopefully. Now, what we did in our current preprint, this is joint work with Josh, Jeremy, and Michael. We have a new curvature-based comparison based on the idea that we want to characterize curvature of a graph at multiple scales. The central premise indeed of our paper is that since the curvature of a graph with this can be a kind of a multi-scale phenomenon, we also need descriptors that are inherently capable of leveraging this multi-scale structure of graph. And this leads us directly to persistent homology and computational topology techniques, namely by the idea that we can borrow ideas from persistent homology and use the curvature of a graph as a so-called filtration function. And the advantage is that we obtain topological representations of the graph, which can be really easily compared with one another, and which, moreover, give rise to certain statistical comparisons that we can't do with other representations and with other measures of the graph, or at least we can't do them as easily. So before we delve into the details of how this looks, I want to give a brief overview of the pipeline here. So first of all, we calculate topological descriptors. We calculate persistence diagrams based on a curvature filtration of the graph. We then convert these persistence diagrams into more suitable representations. In our case, these are persistence landscapes, but you can think about this as some other descriptor that works best and that can be embedded in a nice space. And then lastly, we compare the different representations using permutation tests, using averages, using distances, and so on. So brief intro to computational topology here. Maybe you've seen this before, but I think it's useful if one repeats this every once in a while. So a filtration is just something that arises from a scalar valued function on a graph. So if we have such a function on the graph, it can be defined on the nodes or on the edges or on both, right? We can filtrate the graph. We can obtain a nested sequence of subgraphs by analyzing the pre-images of F. So in this case, I take the degrees of the graph of every node, and then we can take a look at all the nodes with a degree up to 0, all the nodes and edges with degree up to 1, with degree up to 2, and with degree up to 3, respectively. And as you can see, this gives you some insight into the growth process of the graph. In particular, this gives you more information about topological features in the graph, because if you look at this guy here, if you look at this graph here, you can only say something about the ordinary Betti numbers of the graph. So it has one connected component and 2 cycles. That's good to know, but it's a very coarse, a very rigid measure of looking at the graph. Whereas if you track topological features alongside this filtration, so here you would say, oh, I have a couple of connected components here. Maybe here you have 0 connected components. Maybe here you have 2. Here you have 4, and so on and so forth. Then this gives you much better insight into how the graph behaves under certain scales, with the idea that the filtration represents some kind of scale along the graph. This idea of tracking things, tracking topological features alongside this filtration has been codified in what is now known as persistent homology, or rather in their descriptors, namely the persistence diagrams. So it turns out that you can calculate topological features. In our case, since we're staying with the graph, these are only connected components and cycles. We can connect them alongside this filtration. And this then leads to a multi-scale topological descriptor, which is known as a persistence diagram. So here are these diagrams shown for this graph, but the actual numbers are not super important here. The basic idea and the takeaway message you should have on this slide is that we take the graph, we assign it a function, we use that function to filtrate the graph, and then we get these descriptors out of there, which tell us something about the creation and destruction of topological features alongside that filtration. Now, for those of you who are in the know, just to drop that here, these persistence diagrams that we get out of there, they are nice. They form a metric space, but certain operations in that metric space are a little bit cumbersome. So for instance, the calculation of averages or of means in this space is a little bit cumbersome, and it's not even unique because you have some Fréchet mean thing to account for and so on. So what people are doing is they are instead mapping these diagrams into yet another space, namely Banach spaces, that make statistical analysis somewhat easier. And these mappings you can get via a transformation into a Betti curve or a persistence landscape. So this maybe I should mention here that I don't want to go too much into details of how these different representations look. So I'd rather want to show you briefly what we can actually do with this representation and with this conversion. So hence, if you're completely unfamiliar or lost here, then please let me know now. I'm gonna wait for a second without changing the slides. Are there any questions here that I could elucidate before showing what we can do with this technique? All right, then, because then I'd rather move on, and because I have a couple of cool things to show you for hypergraphs as well. And I think that these results are basically somewhat preliminary anyway. They just give you a taste of what works in this realm, and I hope that they convince you that this is useful to do. So the first thing that I want to tell you is that these curvature filtrations that we can build, they are actually expressive in the following sense. Suppose you take two graphs that are strongly regular, so they have regularity conditions on the neighborhoods. These graphs are known to be very, very hard to distinguish with existing methods in graph machine learning. So what we are looking at is, what is the success rate of distinguishing between different graphs if we either use the raw curvature values of the graph or the filtration-based distance of the respective topological features alongside that graph. And what you can see is that in all the cases that we have for all these different data sets, these are different strongly regular graphs with different number of vertices and so on. They are nicely enumerated by other people. That's really great that we have this resource. We can find that in all the cases, our success rate only ever goes up. So either we are already capable of distinguishing pretty much everything, or in this case, 78% of all the pairs of graphs, but this goes up to 89% for the filtration-based calculation. So this is already off to a good start, because it tells us that adding this filtration as an additional component, so adding the multi-scale aspect of our data is already helpful and leads already to improved results. They also turn out to be good in substructure counting. So this is another task that is often relevant for the comparison of different graph generative models. You take a graph, you look at its substructures and how many triangles does it have, how many stars does it have, and so on and so forth. And this gives you a way to distinguish different graph distributions later on. And also here, the filtration values, so the filtration-based distances that we get based on curvature, turn out to be better than the raw values, than the ordinary raw values that we get when we look at curvature as a characteristic property of the graph. In particular, this seems to work nicely for triangles and tailed triangles in these graphs, but there's still, of course, something to overcome here for stars and for cycles and so on. I'm mentioning that this is really preliminary research. We are still evaluating what other failure cases there are and how to improve the expressivity. But overall, I would say that this points towards curvature being a useful property for the comparison of graph generative models. Now, this brings me to the last part. And this is work that is going to be shown at the ICLR conference, or the ICLR conference, if you will, in May, so relatively soon. This is joint work with Corinna and Sebastian, and it's about a framework for Ollivier-Ricci curvature on hypergraphs. So we're already going from graphs to hypergraphs, but the conceptual ideas will remain the same. And I will also show you why I think it makes sense to consider hypergraphs as first order citizens, in first class citizens in this landscape. Because consider this, if you have a graph, you can only model pairwise interactions. Of course, we know we can go to a simplicial complex, and then you can model something else, but simplicial complexes have very strong regularity conditions because you need to have the closure on the faces and so on. Whereas with the hypergraph, we don't have these restrictions. A hypergraph is just a tuple of vertices V and hyperedges which arise from the power set of all vertices. So in that sense, graphs and simplicial complexes can be seen as very specific, very regular types of hypergraphs. Now, that my name is on the slide here, along with a couple of my esteemed collaborators, friends, and colleagues, because hypergraphs help you to capture higher order relationships better than ordinary graphs. What you will find, and I'm very happy to go on record with this, what you will find that some people are doing in network analysis contexts is they take these co-author networks by saying we connect two authors if they are on the same paper or something like this. This is nice and good, but it gives you only a very coarse and imprecise overview of the collaborations, because as you can see here, if we instead model each paper as a hyperedge, so as a subset of the power set, we gain different insights. So for instance, you can see that I'm, of course, I took this from my own bibliography, so this is why I'm on all these papers, right? I'm kind of connecting these two communities, if you will, of authors, but they never had a paper with each other. And also, some of the other people didn't have a paper with some of the other some of the other folks inside these edges. So enumerating and disentangling these types of relations is something that we can only do with hypergraphs, which is why I believe, and my collaborators believe that as well, that these are the right way of looking at very complicated higher order relationship data. Now, back to our previous question, how should curvature actually be defined for hypergraphs? To give you a brief recall on the measure in the graph setting. The graph setting, everything was relatively easy. We have this transportation distance, W1, so the Wasserstein distance, first order. We have probability measures, mu I, mu j, and we have this shortest path distance. Now, for a hyper edge, it's a little bit more complicated. We need some leeway there, but maybe going from the left to right, you can see what we came up with and why we think that this makes sense. Namely, for any hyper edge E, so a set of vertices, we define their curvature to be this expression here. So 1 minus an aggregation function defined along the edge divided by a distance function, some set, or some kind of diameter function, if you will, of this specific edge. So here, our distance or diameter is just the maximum of all the distances of pairs within that edge, and we take the shortest path distance along the edges, along the vertices as usual. The interesting thing comes by thinking about which aggregation functions to choose in practice. So it turns out that since it's a hyper edge, right, we have many more interactions and many more vertices than in the ordinary edge case. So we came up with a couple of aggregation functions. I'm only going to show you two, which I believe make a lot of sense in this context and which have some nice properties. The first one is the average aggregation. So here we aggregate by going over all the subsets of two probability measures of two vertices in our edge, and then we average this accordingly. The other equation or the other aggregation function is the maximum aggregation function. This one is even in some sense more dear to my heart because it is the worst case, the kind of bottleneck through which you have to force your curvature in any case. So it's the worst distance that you can have alongside those edges, and so it's defined as the maximum over all the pairwise edges that you have in your hyper edge. Now, with this, we now have to pick our probability measures, of course, right? Because the probability measure turned out to be critical and crucial for the graph case. So we could guess that it's even more relevant for the hypergraph case. And this is also where we find that there's lots of potential for new research and lots of potential for new models, actually. Because if we start with a neighborhood here in a hypergraph, there's a lot of different ways, and these are only 3 of them, right? There could probably be a lot more of defining a random walk or of defining a probability measure alongside this hypergraph. The first and simplest probability measure uses the equal nodes probability. So this is, you just take all the nodes that you can reach with your hyper edge, with your neighborhood, and then you just go there with equal probability. So completely uniform smoothing, right? The other thing is you could pick your edges, regardless of their size, with equal probability, and then go to the nodes, again, uniformly at random. This gives you a little bit more leeway and provides you with an option to give different weights to vertices that occur in multiple edges and so on. But what you could also do, and this is the most general or the most relevant edge probability measure that we find, is you could weight the edges according to their cardinality. So you could sort of say, I'm much more likely to jump from my paper to a paper that has lots of other authors than to a paper that has fewer authors. Of course, you can also make this weighted edges thing depend on another attribute, on another characteristic of that edge, but let's just leave it like this for now. And with these, you have a couple of aggregation functions and a couple of probability measures to pick. Now the question is, what can we do with this? Well, where does this all lead? What can we say about the choices of these functions and about the implications they have for analyzing the graph? One thing we can say, and it's really, really nice, I think, is that hypergraph curvature is actually really a proper mathematical generalization of graph curvature, in the sense that there are also model spaces or model hypergraphs in this case for negative, 0, and positive curvature. respectively. In our case, these are hypertrees, hypergrids, and hyperclicks, respectively. So this is really, really nice that this intuition carries forward into the graph curvature, into the hypergraph curvature case. Moreover, we can obtain simple upper and lower bounds for these measures, so we know that they are kind of well behaved. In particular, these lower bounds just need a simple total variation distance and a diameter bound on the hypergraphs, which are easy to get. We also can show that curvature relates local and global properties of the hypergraph by deriving something like a Bonnet-Myers type of theorem. Don't want to stress the mathematical details behind this too much, but if we assume that our curvatures are strictly positive and we have some kind of aggregation condition, and then we can actually bound the diameter of any edge, of any hyperedge, or in this case, any subset of nodes. So it can either be a hyperedge in the graph or something different. We can bound this based on the hypergraph Ollivier-Ricci curvature measure that we use, and some kind of expression depending only on the Wasserstein distance, on the transportation distance between the respective probability measures. Now, this is really nice because it really tells us that we are that we can derive these type of characteristic properties from just the local measurements. And towards the end, I briefly want to show you two cool results that we can build with this. So first of all, we find that hypergraph curvature is really discriminative for certain types of collaboration networks, or I should say collaboration hypergraphs, right? So when we build hypergraphs based on the authorships of the American Physical Society papers, we find that different journals or different collections exhibit distinct curvature patterns. So we can already see that we seem to capture some kind of underlying differences in potentially the collaboration or co-publication culture in these types of journals. This, by the way, happens for different types of random walks. Here you can see on the left-hand side, you have the curvature distributions for the equal edges random walk, and on the right-hand side, you have the weighted edges random walk. The other thing, and that's just a glimpse of what one can do now, is that hypergraph curvature can be used to lead to interpretable embeddings of such a graph. And that's a really interesting thing to think about for us. So if we build hypergraphs based on questions on a Stack Overflow forum, so we have the vertices being the tags of a question and the edges are the questions themselves, then we can use a simple RBF kernel, so a radial basis function kernel, between the respective curvature distributions, and we can embed those using a kernel embedding. And then we already find that without adding any supervised label information to that, so these labels are only added after the fact, they're not added during the calculation, mind you, right? We can find that we get a very nice clustering, almost like a very nice almost continuous embedding in which certain parts of the Stack Overflow forum landscape are being clustered alongside each other. So for instance, there's a large cluster of religion-based discussion forums which have some closeness to real-world languages, and of course to older languages like Latin, or maybe I should say dead languages. So this is really nice. Then we have, of course, a clustering of certain, we call them nerd activities, so sci-fi board games and gaming and so on. They're a little bit far out there, but they have some overlap with questions from specific languages, for instance. And so this really gives you a nice way of visualizing such a data set and having embeddings that are to a certain type, to a certain extent, these embeddings are kind of interpretable, because you can analyze them later on. And all of this is done in a purely unsupervised fashion, I should say. Now, there's tons of more to do, but I'm going to stop here and rather want to mention some kind of limitations, some kind of things in which we currently stand. So first of all, the calculations of hypergraph curvature and also of graph curvature, of course, they don't scale very well with the increasing number of edges, because you have to do this for all the edges that you have, right? So approximations are definitely required and will be very much appreciated if we have them. Then likewise, we know that curvature is also somehow oblivious to the attributes of the respective hypergraphs. So it is a purely in a sense, topological property, right? It only includes information about the probability measures, about the random walks alongside that. It has no notion of edge attributes that might exist there, some kind of, I don't know, additional weightings or additional features and so on. This is something that one may want to incorporate at some point. And moreover, we are only working with very localized probability measures. I mentioned that this is because curvature is in itself seen to be a very local property. But in the case of a hypergraph, or also in the case of graph, it might be useful to consider a larger receptive field, because frankly put, it's not unclear that that just having an edge really tells you that everything is local in the graph. It could very well be that you have some kind of underlying geometry that the graph attempts to model. Now, to summarize, I still believe that despite these limitations, curvature can be expressive and useful for graph learning tasks and hypergraph learning tasks. There's two applications that I showed you for this. In particular, what I appreciate about curvature is that it provides you with a complementary multi-scale perspective on both graphs and graph distributions. This is really nice, and we can't get this in simpler terms, to my understanding. However, even in this more structured setting of graphs, so even in this simpler setting, I should say, there are a lot of non-canonical choices to be made. So non-canonical choices, they always give me a headache a little bit, because, well, we could have chosen differently, right? So where does this actually lead us? And I think that moving forward, we need to study the implications of these choices, and we need to see what we actually get from changing them and from moving forward with this. Right. That's all I have. Thank you very much for your attention, and thank you very much for my great collaborators on this talk. I mentioned them already in the papers, but I'm very happy to also send you the slides and more materials about this work. Thank you very much.